What functions f are equal to their third derivative? In other words, can you find all the functions f such that the third derivative of f is equal to f? And why are these functions not better known? It is very well known that the first derivative of e to the x is e to the x. And in fact, all the functions whose first derivative is itself are the constant multiples of e to the x. Similarly, the second derivative of the hyperbolic sine is the hyperbolic sine, the second derivative of the hyperbolic cosine is the hyperbolic cosine, and the linear combinations of hyperbolic sine and cosine are those functions whose second derivative is itself. Also, we know that the fourth derivative of sine is sine, the fourth derivative of cosine is cosine, and linear combinations of these two also have that property. So, where are the functions that the third derivative is equal to the function itself? We can use the theory of differential equations to solve this problem, because we want to solve this differential equation, which is the third derivative minus f equals 0. That is a homogeneous differential equation with constant coefficients, and there is a big theory of how to solve these things. So the theory of differential equations tells me there's going to be a three-dimensional solution. So there's going to be three functions f1, f2, f3, such that the constant multiples of those functions and their linear combinations are all the possible solutions to this. So how do we find what are these functions? Typically, the first thing you do is try exponential solutions. So let's see if f of x is a constant k, e to the lambda x, and lambda is another constant. Let's see which ones satisfy the differential equation. If I take the third derivative, I get k times lambda cubed e to the lambda x, and if these two are the same, lambda cubed must be 1. Therefore, lambda is what we call a third root of unity, so there are three possibilities. Lambda is 1, or lambda is one of the two complex numbers that are solutions to this polynomial. That gives me that there are three linearly independent solutions to my differential equation, which is e to the x, which is sort of cheating because this already, the first derivative is already itself, so this is not a very interesting solution. But then there are two other solutions that are more interesting, and the linear combinations of all three are all the possible solutions. However, this one and that one are complex valued solutions, and I'm looking for real valued functions. This is my full solution of my differential equation in terms of, well, some complex valued functions and constants k1, k2, k3, and rho here is a third root of unity, a complex third root of unity. And I'm looking for those in this family that are real valued. Those will be the functions that are its own complex conjugate, so I have to take the complex conjugate of f. This is a real valued function, so when I take the complex conjugate, I get itself. But when I take the complex conjugate of this, it turns out I get the one with a rho squared. And when I take the complex conjugate of this function, I get a rho in the exponent. And therefore, if these two are the same, then k2 must be equal to k3. And what I get is that the full solution of the real valued functions that are their own third derivative is a constant of e to the x plus a constant times this sum of exponentials. But you see that this function is represented in terms of complex valued functions, even though the result is a real valued function. So what you can do is use Euler's formula here to get other functions that are actually all clearly real valued. So anyway, here are two functions that are their own third derivative, and any linear combination of this one with a sine and this one with a cosine have that very nice property that their third derivative is itself.